Hello everyone. Thank you for having me at the IREC exhibit 2021. I am Aida Younes, a fourth-year PhD student in a co-direction program between l'Université du Littoral Côte d'Opale in France and the University of Balamand in Lebanon. I am going to present my work under the title Valorization of Plastics in the Presence of Ruthenium Nickel on Alumina Catalysts to Produce Syngas. I will start by introducing a general overview of plastics, talk about their dry reforming reaction, and specifically focus on the polypropylene plastics. I will present the catalyst used for the study and the test setup and conditions. I will show the results obtained regarding the catalytic performance and the characterization of the used catalyst, followed by a brief discussion and a conclusion. In recent years, the production and consumption of material plastics have grown considerably around the world due to their low cost, ease of manufacturing, their versatility, and their use in a wide range of applications. Where the main sectors of applications include packaging, building and construction, automotive, electrical and electronics, household leisure and sports, agriculture, and other applications like medical equipment. The plastics produced worldwide in 2019 account for around 368 million tons, out of which 58 million tons were recorded for Europe. Out of the 29.1 million tons of plastic post-consumer waste collected in Europe in the year 2019, 43% are used in energy recovery, 32% recycled. However, the remaining 25% are still sent to landfills. The intensive use of plastics and the high percentage of landfilling present major environmental risks and potential risks to the health of aquatic and terrestrial animals, due to the accumulation in marine debris, in addition to air pollution resulting from the uncontrollable incinerations of such wastes that releases hazardous chemicals. Therefore, the objective of our work is to tackle the non-recycled plastic waste issue while valorizing the greenhouse gas carbon dioxide, to optimize the reaction parameters in order to convert the plastic into syngas. This is done by using an efficient catalyst. The following is the dry reforming reaction of plastics. As we can see, by using this reaction, we will be getting rid of plastic wastes while mitigating the greenhouse gas carbon dioxide and producing synthesized gas, also known as syngas, which is a combination of hydrogen and carbon monoxide and could be used as a raw material for different types of reactions. However, this reaction is highly endothermic and needs high temperatures to operate. It is kinetically limited and needs a catalyst. Moreover, other side reactions could occur, such as methane decomposition and boudoir reaction, that could lead to the formation of coke and thus the deactivation of the catalyst. Today, I will present the results obtained from the pyrolysis dry reforming of polypropylene plastic. Based on this reaction, 2 grams of plastics, which is the quantity used in the test, require 6.2 grams of carbon dioxide and should theoretically produce 210 millimole per gram of syngas and 0.14 moles of hydrogen. For the characterization of the polypropylene plastic, the thermal analysis study in an inert atmosphere showed that the pyrolysis starts at 350 degrees and ends at 510, which will take 32 minutes. Therefore, the carbon dioxide should be sent during these 32 minutes, and that's how we were able to calculate the amount of carbon dioxide needed for our reaction. When the flash pyrolysis of polypropylene followed by GCMS was done, the following pyrogram was obtained, showing the peak degradation, the monomer, in addition to the dimer, trimer, tetramer, and so on. The formation of the peaks could be explained due to the random chain scission of polypropylene, which produces the monomer propene in addition to oligomers. For the preparation of the catalyst, The nickel was impregnated via wet impregnation on the stabilized support using the precursor nickel nitrate hexahydrated and varying the percentages from 5 to 50%. The catalysts were then calcined at 800 degrees. For the promotion of the catalyst with ruthenium, the precursor ruthenium nitrosyl nitrate was co-impregnated with the nickel precursor, and the catalysts were also calcined at 800. All of the fresh catalysts were characterized using TPR, XRD, porosimetry, and PET, and the spent catalysts were characterized by DSCTG. The pyrolysis dry reforming experiment with polypropylene involved two-stage fixed-bed reactors. The first stage containing the pyrolysis reactor consisted of the pyrolysis of the polypropylene, and the product pyrolysis gases were transferred into a second stage reactor where the dry reforming of the produced hydrocarbons occurred in the presence of a catalyst and carbon dioxide. Argon was used as a carrier gas, and the gaseous products after the two-stage pyrolysis reforming process were sent into two gas bubblers, cooled with ice to trap the tar produced. The non-condensed gases were then passed into a flow controller that totalized the volume of the gas collected in a 25-liter Tedlar gas sample bag for post-offline analysis. The results of the pyrolysis dry reforming of polypropylene over different percentages of nickel on alumina show that the number of moles of hydrogen produced and the syngas produced increase with the active phase loading. We can conclude that the more nickel loaded, the better activity for the dry reforming of polypropylene. Moreover, we can notice that the number of moles of hydrogen and syngas for 25, 35, and 50% nickel on alumina are approximately the same. From an economical point of view, using lower nickel loadings while maintaining the best conversion is considered the optimum catalyst for our reaction. Therefore, we can conclude that the 25% nickel on alumina is a promising catalyst for the dry reforming of polypropylene. Since the previous catalytic results show that 25 weight percent nickel on alumina have the best activity, we decided to dope up till this percentage with 1% ruthenium to see if it will further improve the catalytic performance. As we can see, the number of moles of hydrogen produced increase in the presence of ruthenium as we increase the nickel loading from 0 to 15%, then slightly decrease with 25% nickel. The same trend applies for the syngas produced. If we compare the DSC profiles of 15% nickel and 1% ruthenium 15% nickel, we notice exothermic peaks above 500, ascribing to the oxidation of filamentous carbon. However, if we compare the weight loss, we can clearly see that the weight loss decrease in the presence of ruthenium. This means that less carbon is deposited on the catalyst surface in the presence of ruthenium. Therefore, if we compare the nickel-based catalyst with the promoted catalyst with ruthenium, we notice that the number of moles of hydrogen and the syngas produced increase with the increase of metal loading and improved in the presence of ruthenium. We can conclude from these results that 25% nickel and 1% ruthenium 15% nickel on alumina support calcined at 800 degrees show potential as catalysts for the dry reforming of polypropylene. Both catalysts were aged to see which is the optimum for our reaction. Therefore, we use the same catalyst 3 times, each time reforming 2 grams of polypropylene. We noticed that the hydrogen production slightly decreased as we used the 25% nickel on alumina more than once. However, for the 1% ruthenium 15% nickel, the hydrogen production remains almost constant. It could be because less carbon is deposited once the catalyst was promoted with ruthenium, and therefore the 25% nickel on alumina was more prone for deactivation. We can conclude that the hydrogen yield increased as we increase the nickel loading, that the addition of 1% ruthenium promoted on our catalyst improved the hydrogen yield and the syngas production. After characterizing our catalyst after test, we noticed that the position of mainly filamentous carbon on the catalyst surface after the dry reforming reaction. However, this amount of carbon deposited decreased in the presence of ruthenium. Therefore, we concluded that 1% ruthenium, 15% nickel on alumina is the most promising catalyst until now for the catalytic dry reforming reaction of polypropylene. I would like to thank you all for your attention. You can find the emails of the authors. If you have any questions, feel free to ask.